To understand Pika Stream 1.0, we have to look past how we normally think about AI video. Traditionally, generating clips meant writing prompts and waiting minutes. Now, we're looking at instantaneous, synchronous data flows that react immediately to live audio. For enterprise applications, the days of batch-processed, high-fidelity video synthesis are largely over. Speed and continuity are replacing pure cinematic polish. Pika Stream 1.0 functions as a foundational user interface layer for AI agents, providing the visual presence necessary for live communication. The objective has shifted away from outputting short, static cinematic loops. The new requirement is creating a sustained, interactive digital presence that can participate in a live environment. This creates a severe technical paradox. To avoid breaking the illusion, the system must generate a continuous 30 frames per second, complete with highly accurate facial movements and lip syncing that perfectly matches the audio input. And it has to render those 30 frames per second fast enough to keep processing latency below the threshold of human conversational awareness. If it lags, the interaction fails. By deconstructing the architecture of Pika Stream, we can see exactly how it separates heavy visual rendering from cognitive reasoning to deploy a functional digital twin directly into a live Google Meet. This specific, real-time visual layer is the ultimate bottleneck. Without it, reasoning text models are trapped as chatbots. With it, they can fully participate in live, human-centric corporate environments. Let's look at the hardware constraint first. Standard video generation models often require several seconds, or even minutes, of heavy compute time just to render a single second of footage. Pika Stream bypasses this bottleneck by optimizing its entire model to run entirely on a single NVIDIA H100 GPU. Pika Stream routes a parallel audio-video pipeline through GPU tensor cores, compressing render time for low-latency synthesis. Supporting this are massive datasets. 10 million pre-training clips teach macro human movements, while 2 million supervised clips train interactive facial behavior, eye contact, and accurate lip syncing. Despite this dual-layer optimization, the current operational beta runs into a strict limit. The system averages a latency of about 0.8 seconds. In a professional communication setting, an 0.8-second lag is highly visible. It disrupts the natural cadence of a back-and-forth conversation. Because human speech relies on split-second timing cues, this specific delay consistently causes awkward mid-sentence interruptions between human participants and the AI agent. Achieving sub-second hardware latency is actually a harder engineering challenge than rendering the video itself. It remains the ultimate barrier to true human-AI parity in live meetings. To maximize speed, Pika Stream's core architecture intentionally lacks any native reasoning capabilities. It doesn't think. Isolating the heavy visual rendering load from the complex cognitive processing is essential. If the model had to formulate answers and draw the face at the same time, the delay would be insurmountable. To bridge this gap between visuals and logic, developers rely on an open-source modular framework known as Pika Skills. This 3-tier framework integrates directly into interfaces like Google Meet. Below that, a local Python environment uses a skill.md manifest file to dictate agent activation. Finally, all cognitive tasks route to the foundational 3rd tier, specialized external reasoning engines like Claude. This modular separation gives enterprise teams total control. They can swap or upgrade their underlying reasoning engines at any time without ever breaking the complex visual rendering pipeline above it. A real-time visual avatar is useless if it suffers from amnesia between meetings. To function as a persistent teammate, it requires stateful memory. Prior to a call, Pika Stream synthesizes specific workspace context directly into the agent's system prompt. It instantly retrieves user identities, past project details, and recent CRM activities, so it can recognize participants by name. But supplying that constant, intelligent presence requires massive capital. Running a real-time synthesis pipeline demands access to highly expensive H100 GPU clusters. This chart illustrates the market economics. A standard human expert consultant costs roughly $1 to $3 per minute. The Pika Stream synthetic avatar costs a fraction of that, operating at around 8 to 12 cents per minute, depending on the required resolution. While significantly cheaper than a human worker, this strict usage-based pricing model requires aggressive automated billing controls to manage the underlying compute costs. Before an avatar joins a meeting, the system scripts perform a real-time API credit check. If funds are insufficient, a failsafe automatically generates a payment link, waiting for the transaction to clear. This completely prevents abrupt administrative drops mid-call. Engineering this robust financial and memory integration is just as critical to actual enterprise deployment as the video rendering technology itself. Right now, Pika Stream 1.0 successfully acts as the bridge between generative video and live agentic workflows. But there are immediate operational risks. The heavy hardware dependency requires local clients to use up to 32 gigabytes of RAM, which currently leads to documented memory leaks in the beta environment. There are also broader friction points. Deploying hyper-realistic digital twins to represent human employees introduces profound ethical implications around consent, identity theft, and potential brand dilution. The immediate engineering priority on their roadmap is clear: optimizing that 0.8-second lag down to near zero to eliminate conversational friction entirely. Looking further ahead, the focus shifts to integrating multimodal reasoning designed specifically for physics simulation, referencing advanced physics-aware models like Void. The agents won't just look human, they will interact accurately with the physical constraints of their digital environments. Synthetic video has become the primary interactive interface for global enterprise automation, providing a face for the complex logic of AI agents.